Hello, it's me again on a nice Sunday afternoon here in Brussels. I'm Jean-Louis Van Belle. I'm a sort of open science researcher into physics, especially quantum physics. In the previous lectures, I demystified a lot of stuff. I think I was actually quite pissed because I did so. Referencing Feynman's lectures and pointing out where I think his explanation is less than satisfactory. Any case, that video got taken offline by the defender of the copyrights on the copyright on Feynman's lectures from 1963. There's still someone holding the copyrights and determining what you can say about them and what not. Any case, I won't do a rant on that. I realized in that video that was taken off and that I then redid sort of without referencing Feynman. I didn't provide really like an easy model of the photon. And I didn't really explain what, when I was criticizing this mathematical concept of spin, what it would be in a realistic model that's consistent with classical physics. So let me do that now. I won't be too long because I will show you where you can find a lot of details. There's a lot of papers out there. But let's first look at this thing here. This is a linearly polarized wave, or at least the image of electric field vector that is oscillating up and down. A nice sinusoidal form. And as we know, that comes with a magnetic field vector, which you see here. We know that the magnitude of the electric field vector is, when you take natural units, time and distance units, is the same as that of the electric field vector, but its phase is, has a delay of 90 degrees, so it's perpendicular. The magnetic field vector is perpendicular to the electric field vector. So what's the spin in this thing? There's no spin. A linearly polarized wave, or the photons that make up that wave, I will say more about that in a moment, they don't have spin. What's a photon anyway? Actually, I should start with that probably, and that will then explain how this image brings together, the concept of wave and a light particle, a photon. Basically, we have two kinds of electromagnetic fields, right? Static fields and dynamic fields. And a static field, at some point in time, at some point in space, we will have an electric field vector and a magnetic field vector. And because the field is static, these won't vary with time. They are a function of space only. So these are static fields. And then we have dynamic fields. And photon is I would say, sort of a special case of a quantized dynamic field. Is the field vectors E and B will vary as a function of time also at some point in space x, y, z. Now, what's a photon? A photon is very special in the sense that we have an electric field vector, which is a function of x, y, z, and t, and we have the magnetic field vector. Both are related, and we can, for vector algebra, that looks even simpler than this. The electric and magnetic field vector for a photon, that's where you can define a wave function, will be zero everywhere, except when the photon happens to be, for instance, here, where we have a magnitude for the magnetic field vector and a magnitude for the electric field vector. And you will see we can sort of, the electric field vector goes up and down, and the magnetic field vector also goes up and down. And the funny thing is that to to define this photon, we could sort of define it by what I call a bivector. We combine the electric and magnetic field vector, we add it up, and you can see this will be sort of, well, you can call it an amplitude or a wave function, and it will go in and out, right, as it travels along its direction of travel. Let me clean up my, okay, my whiteboard. So you will say now, well, that's kind of funny because at certain points, like here, you know, your electric and your magnetic field vector are 0. So then there's this photon has no energy. How does that? How is this consistent with the energy conservation law? That's sort of the questions, you know, you ask as a student, and me too. And that's really where, yeah, that's sort of a mental leap you have to take and swallow the idea, I would say, of the quantization of you know, light particles and matter particles. They are periodic phenomena, as Louis de Broglie called it. Light particles, photons, we knew that quite from the start, but matter particles as well. And so that's where you say, like, yes, a photon is at one point in time, at one point in space only, but at the same time, you know, it is a unit. It has a particle-like character in the sense that this oscillation packs a certain amount of energy. And if it has spin, I will come back to that. In this case, it has no spin. It will pack a certain amount of angular momentum, but it surely packs a certain amount of energy. And yeah, that's sort of the mental leap you have to take, where yeah, photon has a definite energy, and if it's going to interact with an electron, it's gonna you know, its energy will go into will mess with the energy of the electron. Or another matter particle, and there it will mess with the charge inside of that matter particle, which is, you know, that distinguishes a photon from a matter particle. Photons carry no charge, but they mess with the electromagnetic field that keeps the charge in a matter particle going and spinning, and which makes matter particles a periodic phenomena as well. This may sound as Chinese or revolutionary, so that's why I quickly will point out. Where are we here? Yeah, I hope you see that. This is sort of my paper, which has a lot of downloads, almost 15,000 now on ResearchGate, and where I do explore that concept of de Broglie's matter wave and how it really works, what electrons, protons really are. They are charge in motion, and that charge in motion has a certain structure, and that structure explains its scale, etc. But I wanted to point it out. His main reasoning from his thesis of 1924, published in 1925. We may conceive that because of some grand law of nature, a periodic phenomenon with a certain frequency would be associated with each energy packet with rest mass m0. So matter particles are basically energy packets. And then he combines Einstein's mass energy equivalence relation, E is mc square, with the Planck-Einstein law for radiation, which says the energy is, you know, Planck's quantum of action times some frequency, nu. And so you have h times nu 0 must be equal to, you know, the energy that is associated with that oscillating thing, that energy packet, and because of the Einstein's mass energy equivalence relationship, that must then be equal to m0 times c square. And the 0 is, of course, because we in m0 we measure the mass of a matter particle in the rest frame of that particle, and so, and then goes on and on and on. And the basic thing where de Broglie went wrong is that he, you know, this frequency, he associated it with a linear frequency, just like a photon. A photon has a linear frequency, but a matter particle has an orbital frequency. In any case, we're talking about photon spin states here, of photons. You can see in this picture, you know, we have a vector going up and down, a bivector, I would say, which is consists really of two vectors, the electric field vector and the magnetic field vector. And I know that here, you can write that bivector because we know that the magnetic field vector is, its magnitude goes up and down with the electric field vector. It's just orthogonal perpendicular to it, so we can write it as E times the imaginary unit times the electric field vector, and then we have an expression like this for this bivector. It's the electric field vector minus the imaginary unit times the field vector. So we get something like this. You will say, what is this? Well, 1 minus E is a complex number. You can see it corresponds to a clockwise rotation by 45 degrees, as we have here, from the electric field vector. And if we multiply, that one complex number, one vector, I would say, with another vector, the electric field vector, then we will also have some magnitude change, which we do see. This bivector has a somewhat smaller magnitude than the electric field vector. But that's math. That's a lot of math. What I wanted to talk about is really, the fact that this one, this is sort of the mystery behind, how you solve the mystery behind one photon Mach-Zehnder interference. If we would have, a circularly linearized photon, then we can split it in, like, I would say, 2 half photons, but this is a full photon, but 2 photons with one photon which has 0 spin, and the rest of the energy then of the full photon, I would say, gets absorbed by the polarizing material. And so, yes, a photon can be split up into sort of two zero-state things. And that's how you explain one photon Mach-Zehnder experience. I refer to my, which one? Yeah, this one, my lecture on quantum behavior, which at the end has that explanation. I will come back to that, because here you can see I'm talking about spin in the context of matter particles, which I haven't. Let's go back to that, circularly polarized photon. What you have there is indeed that, electric field vector. We could also have taken the magnetic field vector, and it goes round and round and round around an axis, right, in the direction of propagation of the photon or the electromagnetic wave that is associated with that photon. Now, the trick to understanding a lot of things is to realize that in an illustration like this, they usually conveniently break down, that vector in, a vertical and a horizontal component. So here we have this one. No horizontal component, but of course, if it's here somewhere, here, then we do have a component in the horizontal direction and a component in the vertical direction. So, but yeah, so there we have spin. We have the spin of the electric field vector. We do not see the magnetic field vector in illustration like this, but of course the magnetic field vector is always there, and it's always perpendicular to the electric field vector. So if that electric field vector spins around, the magnetic field vector spins around as well. And so that's where, you have this bivector, E and B, spinning around, and it spins either around in this direction or in the opposite direction. So that gives it its spin up or down. So that's actually sort of all the magic there is to it. I'll probably close my thing. The thing is sort of, I'm still looking for like a mathematical framework to sort of replace, I wouldn't say replace the amplitude math that we have. but to demystify it. And I think the secret is indeed in sort of developing some kind of what Hessens calls a space-time algebra, which works effectively with bivectors, and then some kind of interaction theory. This is something I also wanted to talk about. I said matter particles. Let me go to matter particles indeed. I said with matter particles, they differ from light particles, neutrinos and photons, because they're oscillating charge and they have a certain structure. And so the concept of spin is very different than for matter particles than for photons. Why? Because we have actually real charge spinning around. It's not a field spin, I would say, but really charge that is spinning around. And the important thing I do, or the breakthrough I had, the aha Erlebnis, if you want, was really that I realized, photons, are point-like, but matter particles, and I'll come back to that, they have a structure. They take up some space, and they take up some space because you have a point-like charge spinning around in that structure, and so that creates a ring current, which generates a magnetic moment mu. I pointed out here. See the equation here, and they have some real angular momentum. That charge has kinetic when it spins around, kinetic energy, and so it has a real angular momentum. And we could take the ratio and sort of then have an idea about how this thing should look like. At the same time, what we can do with matter particles is they have a rest mass, and they have a certain elementary charge, +1 or -1. And so the +1 or -1 is different in an electron and proton because they have a very different rest mass. So the structure of that oscillation must be very different than it is, two-dimensional and three-dimensional oscillations, we think. So, but you can have that ratio Q, how much charge is there for each unit of mass, and that differs. That's a different thing for electrons and protons. That's where the charge or the charge structure must be different. And so you have this deep mystical concept in quantum mechanics, the way it is being taught traditionally, the G ratio, which says, for matter particles, we can take these two ratios, mu divided by L, the magnetic moment divided by the angular momentum, and then Q divided by M. And then, to see how these two ratios are proportional or relate to each other, then we have this G ratio. I think it's a pretty useless concept, and I will explain why. So it doesn't clarify very much. What I find interesting is to see that here, for an electron, we can indeed have two ratios, inverse or the way I write them here. The mass mass charge ratio, Q divided by M or M divided by Q here, and then the magnetic moment with the angular momentum. And then when you see in these models I develop, an electron has a two-dimensional oscillation of charge. I have a certain formula. Half of the energy is in the kinetic energy of the charge oscillating about, and the other half is in the electromagnetic field that this oscillating charge generates, and which keeps it in its orbit. I have that formula for the magnetic moment that this ring current generates, and it's the elementary charge times h bar divided by 2 times the mass of the electron. This 1/2 factor is related to the energy partition theorem, which says indeed half of the energy the equivalent mass of the electron must be in the kinetic energy, and the other in the electromagnetic field that keeps it going. And I can do that for a muon. For a proton, we think of it as a three-dimensional oscillation, so we have a 4 factor there. You always arrive at this ratio, m times mu over q times the angular momentum L will be 1/2. And that's sort of this mystical thing where they say matter particles are fermions or spin 1/2, because the only meaningful the G factor is always the same. It's 1/2, and that G factor, what is it? I will write it on top of the page. If we write mu the magnetic moment divided by the angular momentum, as some factor times q divided by m, we necessarily arrive at a factor 1/2 for all elementary matter particles. The formula works quite well for a muon electron as well. Not quite, but that's because a muon electron isn't stable, so there's something that makes it disintegrate, and that something is that the oscillation is a bit off, doesn't quite respect the Planck-Einstein relation, etc., etc. In any case, you can find that in that paper on quantum behavior. The other thing I wanted to work out was maybe, I have a blog. You often hear about this mystical Bose-Einstein behavior and Fermi-Dirac distributions or behavior. There's no real miracle in that, in the sense that if you go to that blog, wrote this in 2015, the difference between matter and light particles is indeed light particles you can pile as many as you want on top of each other. These photons are effectively point-like, although they have a unit structure, but one photon can be on top of another photon, and you can add another one. While for matter particles, they take up space. And the only way you can put two electrons, let's say, on top of each other is if their spin is opposite, and then there will be some complicated geometrical dance with each other, where the two charges will be opposite of each other, because the like charges reject each other, but they will still be lowering their energy and having total energy. If, this is why this whole chemistry is based on that. We have spin up and down in one suborbital or energy state. And so, Fermi-Dirac statistics are really a matter of acknowledging that you can only have, as I show here in this picture, two particles in one energy state, and then you can have here in this example we have 1, 2, 3, 4, 5, 6 particles, and we have 9 possible energy states. So you can sort of distribute that, but it's pure I would say combinatorial math. You can distribute these like you want over the 9 energy states, but there's a restriction that you cannot put more than 2 of these particles in one energy state. And so that's where where these Fermi-Dirac mathematics or statistics come out of. And there's nothing more to it, and this is also where I'm going to stop referring to MIT and Feynman and whatever. I'm very grateful, and I'm going to acknowledge the hyperphysics website of Georgia State University is probably a very good place to learn about quantum physics if you really want to learn how things work, rather than swallow the metamagical games of Richard Feynman. So sorry for taking a bit of revenge and representing I would say Einstein's view, where he also said that God doesn't play dice, and especially, and I'm probably going to end with that, quoting the successor of Hendrik Anton Lorentz. Where is it here? You can read that. Ehrenfest, he committed suicide because he couldn't cope anymore with what he referred to as der unendliche Heisenberg, Born, Dirac, Schrödinger, Wurstmaschinenphysikbetrieb. So we don't want to end up like he did. He committed suicide. I wrote on my blog about that. I think it is because indeed he was very tired of what is, indeed some kind of metamagical games, making general public feel that they will never quite understand it. I don't think that's the case. I think everything is quite logical. You will say, well, what about high energy physics? There I would like, and quarks and gluons and all that stuff. I would like to remind, it's true. I haven't dug much into that. One reason is that I think you're really modeling unstable combinations of fields and charge there that are really very, very difficult. It's disequilibrium math and disequilibrium statistics. And so I do think that, with these flavor numbers and other, weird quantum numbers, not QED quantum numbers, but the idea of quarks and stuff. You can sort of model that mathematically, simplify it. It's sort of a factoring of what probably goes on. But I do believe the normal laws of physics are at work there. And with the normal laws of physics, I mean what I put somewhere here, I think. Yeah, Maxwell's equations that sort of break down at the smallest level because, they talk about charge densities, and when you start talking about an individual charge, that that is kind of difficult to apply Maxwell's equations. But when you combine them with the Planck-Einstein relation, then you see what quantization really is about, and what Planck's quantum of action, a product over a force over some time, over some distance, that dictates how energy, linear angular momentum, is discrete, how it gets packed, so to say, into a light particle or a matter particle. Yeah, that all makes sense. So quantum mechanics is, or all of physics, I would say, is no mystery. It's Maxwell's equations plus, really understanding what the Planck-Einstein relation is about. So, yeah, I refer you to my papers now, and I will stop talking and go for a nice bicycle ride in the sun. Thank you.